Again, good morning, good afternoon, or good evening to everyone. And let's start with this third session dedicated to the next decade of black hole. And today we will talk about fundamental physics. I want to just remind you before starting that if you have any question, please raise your hand, or alternatively, you can ask a question via chat. The first speaker is Enrico Barausse with the Black Hole Beyond GR. Please, Enrico.
Well, thank you, Mariafelicia, and thank you thanks to the organizers for inviting me. So today I'll be talking about black holes beyond GR. This is let's see if I can change slide. So here's a brief outline of the talk. I will try to motivate why we want to go beyond GR. And also I'll try to explain very briefly how we go beyond GR. So after this introductory part, I will start by describing how deviations from GR affect the dynamics of black hole binaries and also to some extent binary neutron stars. And this will lead me to discuss constraints that you can put on deviations from GR using gravitational waves, in particular the spiral. And I will make a connection also to constraints that you can place with the Event Horizon Telescope. I will then move forward higher in frequency, and we talk about constraints that you can place on black hole geometries and deviations from GR using the ring down phase of a gravitational wave, a binary merger. And I will again draw a comparison to constraints that you can place with the Event Horizon Telescope. So we'll draw a parallel, if you want, between quasi-normal modes and black hole shadows. Something that I wanted to cover in this talk, but for which I didn't have any time, are effects that can take place near the horizon, like firewall, super-radiance, violations of Lorentz symmetry, and so on and so forth. However, Paolo and Mina in the next two talks will talk about that, so it's not too bad. So first of all, how do we go? Why do we want to go beyond GR? There are several, of course, reasons why we entertain the possibility of deviations away from general relativity, and the most obvious one is that GR is not a UV complete theory. It's not renormalizable, even power counting renormalizable. So it needs to be completed at high energy into a full theory of quantum gravity. Typically, however, these deviations from GR that take place, that appear at high energies, are not very important for black holes unless you go very close to the event horizon. So again, I believe Paolo and Mina in their talks will talk about near horizon effects. However, if you're interested, I mean, I can address that in the discussion session. So more relevant for us, however, is the fact that there is, of course, evidence from cosmology for a dark sector, dark energy and dark matter, on very large scales in the infrared. And these effects may actually be a signal of a possible breakdown of our understanding of gravity on large scales. So they could be due to a modification of the gravitational theory. And thirdly, another reason why we should entertain the possibility of modifying or extending general relativity is that general relativity, until the LIGO-Virgo detection of black hole binaries and binary neutron stars, had only been tested in regimes of mildly relativistic velocities in weak gravitational fields. And this is what I try to show in this plot, where I show a bunch of observables, cosmological observables, such as the CMB or the Milky Way or solar system observables, and they all lie at very small velocities compared to the speed of light and very small strengths of the Newtonian gravitational field U. Whereas with gravitational waves, I hope you can see my cursor, by the way, should have checked that. With gravitational waves, we manage to impinge on this region of parameter space, which corresponds to strong gravitational fields and very relativistic velocities. So this is, I hope I've convinced you about why we go beyond GR. So as to how we go beyond GR, that's a complicated question that would deserve a talk by itself, and which I try here to summarize in a single slide in this chart. So a guideline or a roadmap to extend the general relativity is provided by Lovelock's theorem. So general relativity is essentially the only gravitational theory that you can think of under a number of assumptions which are stated in Lovelock's theorem, which you can violate one by one. So I don't want to enter into the details about how you violate these assumptions. Let me emphasize just 2 or 3 points. First is that virtually any modification of GR that I'm aware of introduces extra polarizations, extra gravitational fields, scalar, vector, or tensor polarizations, besides the tensor polarizations of the gravitational field in GR. And that these extra polarizations, even though they don't couple directly to matter, even if they couple only to the metric, because the metric is a dynamical object in any relativistic theory, the metric can mediate an effective interaction between matter and these extra fields. So you can think of these extra polarizations as not coupled to matter at 3 level, but when you go to next order perturbation theory, an effective coupling to matter reappears, mediated by the tensor fields. And this introduces what we call sometimes fifth forces, that is violations, if you want, of the strong equivalence principle. So if you have a system of 2 black holes in a theory that deviates from general relativity, this system of 2 black holes will move differently than a system of 2-point particles with the same mass. This is not true in general relativity. So a system of 2 black holes will move on the same orbit as a system of 2-point particles, at least if the separation between the 2 black holes is large. Here there will be fifth forces that break, if you want, the universality of free fall that we know is satisfied in general relativity, what we call the equivalence principle. So let me say a couple more words about these violations of the strong equivalence principle, because they are key to understanding how we test these deviations from general relativity, whatever their nature. So the fact that when you go beyond GR, you violate the universality of free fall, the equivalence principle for strongly gravitating objects, was discovered early on by Dicke in 1969. And it was discovered in the particular setup of what we call nowadays Fierz-Jordan-Brans-Dicke theory, which is a very specific gravitational theory in which you not only have the tensor gravitons of general relativity, but also an additional degree of freedom, a scalar field phi. So the action for this theory is what I write here. And as you can see, the scalar field enters in a very specific way in the action. In particular, it renormalizes the Planck mass, or if you want, it renormalizes the Newtonian gravitational constant that appears as a prefactor to the gravitational action in general relativity. So this has a profound effect because, of course, big G, the Newtonian gravitational constant, enters in not only the Newtonian interaction, but also in what we call the gravitational binding energy of an object. So for instance, if you have a neutron star, about 10% of the mass of the star is actually not in baryonic components, but it actually comes from the gravitational binding energy of the star, which is, of course, dependent upon big G, the Newtonian gravitational constant. So in this theory, the Newtonian gravitational constant, or the Planck mass, becomes position dependent, and in particular depends on the local value of the scalar field. As a result, the mass of the star will not be, unlike in GR, constant anymore, but will be a function of the local value of the field. And this is what I wrote here in the last line. Of course, this effect will be increasingly important for more and more important the more the star is compact, because for a star like the Sun, the gravitational binding energy contributes a negligible part of the mass of the star. However, for strongly gravitating objects such as neutron stars and black holes, the contribution of the binding energy to the mass will be significant, and therefore the mass will be a function of the local value of the scalar field, which allows for writing an action like this, in which you model a star with a point particle with a mass which is not constant. And as you know from GR, if you vary a point particle action, you get the equations of motion of the star. And in this case here, you not get the geodesic equation as you would in GR, because on the right-hand side, you would have derivatives of the mass of the star with respect to the scalar field. And this is what we call, in somewhat technical jargon, sensitivities, or scalar charges or hairs. So they're a measurement of how the mass of the star or the black hole changes as a response to changes in the environment or the boundary conditions in theories of gravity. In this case, in scalar tensor theories, the Brans-Dicke type, but we can write similar expressions in any modified theory of gravity. So the point I want to convey with this slide is that the geodesic equation doesn't describe the motion of strongly gravitating objects beyond general relativity because of the presence of these black hole or neutron star hairs or sensitivities. And this has profound implications for gravitational wave emission, because whenever you violate the strong equivalence principle, you start producing additional multipolar, additional multiples for your gravitational wave signal. In particular, you produce monopolar and dipolar radiation, which are forbidden in GR because of conservation of the stress energy tensor. In fact, in GR, the situation is very similar to the one you have in electromagnetism. In electromagnetism, you have no monopolar electromagnetic radiation because the Maxwell equations imply conservation of the electric charge. Similarly, in general relativity, you have no monopolar or dipolar radiation because energy and linear momentum are conserved because of the Bianchi identity. In fact, if you were to try to write a dipole, say a dipole gravitational wave signal simply based on dimensional analysis in general relativity, you would write something like this. So H, G over C to the 3 times the mass dipole, the time derivative of the mass dipole M1. And, but if you calculate the time derivative of M1 of this quantity, you will find that the time derivative of the mass dipole is simply the linear momentum, which is conserved. So if you try to write down a dipolar gravitational wave in general relativity, you don't get a wave, you just get a static Newtonian-like potential that decays as 1 over r. So it doesn't carry any energy. And so in extensions to general relativity, this is drastically modified in the sense that if you try to redo this cartoon dimensional calculation and write down the derivative of the mass dipole in a theory of gravity that deviates from GR, you would have derivatives of this mass dipole M1 x1 plus M2 x2. And here in particular, you would have derivatives of the masses, which are not constant anymore. And this, in fact, you can do this calculation more precisely. And what you would find is that dipole gravitational wave emission in beyond general relativity is non-zero, and in general scales as the difference of the scalar charges or sensitivities of the two objects you consider in your theory. And this is a very important effect because, in fact, it's dominant over the usual quadrupolar emission of general relativity in the Early spiral of gravitational wave emitting systems, because it appears, in fact, at what we call -1 PN order. So it's a low frequency effect that can potentially overshadow the gravitational, the quadrupolar gravitational wave emission of GR. And in fact, this is an effect that has been studied for decades in the context of binary pulsars. Binary pulsars have been observed, and they show no evidence of dipolar gravitational wave emission. In fact, the period damping of binary pulsar starting from the Hals-Taylor pulsar, which was the first that was observed, is in perfect agreement with the quadrupole formula of general relativity. So there is no evidence of dipolar emission in binary pulsars, and this allows to put constraints on the sensitivities of neutron stars, and has been historically used as a way to bound deviations away from general relativity. So So what we can do today with LIGO is instead extend, LIGO and Virgo, is to extend what has been done for binary pulsars to black hole binaries. So the class of theories that you can constrain with black hole binaries is actually orthogonal in a sense to the one you can constrain with binary pulsars. So binary pulsars have been historically used to study scalar tensor theories or to constrain scalar tensor theories of the Brans-Dicke type, which predict that neutron stars should have hairs and black holes should have no hairs. So there are no hair theorems in Brans-Dicke type scalar tensor theories. So it's not a surprise that, again, neutron stars can have hair and black holes don't, because the equivalence principle is modified. So the equivalence principle tells you that the motion of objects is not universal, but depends on their nature. So in these theories, the motion of black holes and neutron stars is intrinsically different. However, there are more general classes of, there are more general theories that deviate from GR, which we can test with black hole binaries. And in fact, if you think of GR as an effective field theory, and if you want to push this effective field theory to higher order, you should include at higher energies terms that are quadratic in curvature. So here I wrote a scalar tensor theory, and I wrote also terms quadratic in curvature. So the first term, the first two terms, f of phi times r, f of phi times r squared, are terms of the Brans-Dicke type. So they produce no hair for black holes. But there are also higher order terms that you can include that include couplings between the scalar field and Riemann, essentially, the Kretschmann invariant, the Pontryagin density, and the Gauss-Bonnet invariant. So to make a long story short, because I'm rapidly running out of my allotted time, such terms in the action, they produce scalar charges for black holes. And if you choose the coupling functions F2, F3, F4 to be generic, to be analytic in phi, and in particular, if you include also a quadratic term in phi, what you find is that the black hole scalar charges can be extremely significant. And this is something that has been studied extensively in the last 2 to 3 years. It's called black hole scalarization. So if you include quadratic terms in these coupling functions, black holes, if you start with a Schwarzschild black hole of general activity in this theory, that black hole would become unstable and would undergo a phase transition to a new vacuum state, which is non-perturbatively different from Schwarzschild or Kerr. So if you include these terms in these curvature-dependent terms, which are quadratic in curvature, black hole geometries can be profoundly different than in general relativity. And this is what we call scalarized black holes. And this scalarization can take place both in the presence of rotation or, as we understood recently, also in the presence of rotations. Okay, so yeah, let me go to the next slide. So I hope I have convinced you that it makes sense to try to use gravitational waves to measure black hole charges, because that provides a gateway to understanding the gravitational theory, and in particular couplings of additional graviton polarizations to curvature. So this has been attempted and is being attempted by the LIGO-Virgo-Cagra collaboration. And in fact, this is a figure that I took from one of the LBC papers, where they put constraints on deviations from GR at different post-Newtonian orders during the black hole binary in spiral. They focus on a few events, the ones with the longest in spiral. And in particular, you see here that the strongest bounds you can place are those on the -1 PN term, which is exactly the dipole emission term that that depends on the charges of on the black hole charges, which I described above. So these are relatively weak bounds for the moment. However, if you had access to a longer in spiral, either by going underground and cryogenic, that is by using third generation detectors such as the Einstein telescope, or by going in space with LISA, we will be able to put constraints on dipolar emission and also on higher PN order effects, which are much more stringent. So this is, for instance, a comparison with constraints that we can put on the dipole flux, the dipole energy flux. This B is the dipole energy flux, as can be constrained today by LIGO, 10 to the minus 2, 10 to the minus 3, as compared to what we will be able to do with LISA and ground-based in joint operations. And for comparison, the dipole flux we can constrain with binary pulsars today amounts to 2 parts in 10 to the 9. So the constraints we'll be able to get on dipole emission from black holes with LISA will be comparable to those that we can place today with binary pulsars. So it will be a massive improvement in an understanding of hair, black hole hair, and a much stronger test of the no-hair theorem of general relativity. So I have 4 more minutes besides the question, so let me go straight on. So where does the ngEHT stand in here? The ngEHT can also attempt to place constraints on at separation. The ngEHT can also place constraints on the metric of black holes, but the constraints the ngEHT can place they don't lie, if you want, near, they lie near the circular photon orbit. So the ngEHT constrains the geometry of black holes only near what we call the light ring, which for Schwarzschild is at 3 gravitational radii, whereas gravitational waving spirals constrain much larger separations. So separations larger than what we call the innermost stable circular orbit of the system. So that lies at 6 gravitational radii for Schwarzschild black holes. So, so there have been attempts by the ngEHT collaboration to place constraints on post-Newtonian parameters. That's a bit tricky to do, as we showed in this paper, because the ngEHT size measurements actually is sensitive to the metric in a region where the PN series is only weakly or slowly converging because you're close to the light ring. So the ngEHT doesn't put constraints on the PN coefficients 1 by 1, but actually put constraints on a linear combination of all post-Newtonian coefficients, potentially an infinite combination of all post-Newtonian coefficients. That doesn't mean, however, that the ngEHT is useless when it comes to test of general relativity. There are theories, in fact, which have an interest potential also for cosmology, which cannot be tested by LIGO and Virgo, and counterintuitively, they can be tested by ngEHT-like experiments. An example is this theory that I showed already before with the coupling between a scalar field and the Gauss-Bonnet invariant. Again, that's one of the terms that you would expect in an effective field theory like expansion of your action. And this is a theory that produces black hole scalarization. So black holes that are non-perturbatively different from general relativity. And it turns out that this theory has a dimension-full free parameter, lambda, and you can find ranges of this dimension-full parameter for which the ngEHT can place constraints because of the larger mass of the black holes it can detect, and LIGO can put no constraints at all. So there is, I think, there are potential synergies between ngEHT and gravitational wave interferometers, be them on ground or in space. So in the last 1 minute, because I don't want to go over time, unlike what I do usually, let me say that there is a also another way of testing gravity using gravitational waves, which is to look at the black hole ring down. And because the beautiful ring down that we observe in the pictures published, in the plots published by LIGO, is actually a superposition of damped sinusoids with frequencies that depend on the mass and spin of the black hole as a result of the ngEHT theorem. So if you have additional hairs in your black hole solution, they will end up affecting the frequencies that enter in the gravitational wave ring down. So this is a test that's been attempted and is being attempted today, perhaps by using higher order overtones, but one that will become much more precise with next generation detectors and LISA, because the signal to noise ratios involved will be much higher. And the reason why I wanted to talk about ring down tests is that there is in fact a one-to-one correspondence between black hole shadows and quasi-normal modes. And in fact, the frequency of the quasi-normal modes that we observe in LIGO and Virgo can actually be written as proportional, at least in the geometric optics limit. So in the high frequency limit, they can be written as proportional to the frequency of the circular photon orbit. So there is actually, and also the imaginary parts, the decay times of those modes are related to the curvature of the effective potential for photons near the light ring. So there is actually a profound physical connection between black hole shadows and black hole quasi-normal modes. So the physics that we test with the ngEHT observations would be, is actually effectively the same, albeit at a different scale in mass. As the physics tested by black hole ring downs. And yeah, I think I'm out of time, so maybe I'll skip this last slide where we try actually to put this program in practice. So we try to combine bounds on parametrized metrics that on parametrized deviations from GR you can place with quasi-normal modes and black hole shadows. And I'll go straight to the conclusions. So what I try to explain in this short talk is that general relativity has already been tightly constrained in the local universe by binary pulsars, the solar system, the spiral, LIGO, Virgo, black hole binaries, but there are still non-perturbative effects that are potentially important, especially for black holes. And this is what I refer to as black hole scalarizations. I didn't end up talking, sorry, about screen of local scales. The ngEHT bounds on the post-Newtonian coefficients, which has been attempted by the collaboration recently, is one way to go forward. It's a bit tricky to do, in my opinion, because the post-Newtonian coefficients are not really well defined near the light ring, so you have to be careful about the generacies. A more promising way forward is to try to combine bounds from the ngEHT and gravitational wave quasi-normal mode ring down bounds. And this could be complementary for some class of theories for which no deviations is measurable in the LIGO band, but which could give sizable deviations on the scales relevant for the ngEHT. And I gave you one example of that theory. So yeah, I think that's all I wanted to say. So I believe I'm almost on time. So I don't know if
yeah, just 2 minutes. In the list, but it's okay. Thank you, Enrico, for your talk. I see Paolo. Do you want to?
Yes, I have a question. Thank you, Enrico. Could you elaborate a bit more on the last thing you said about the fact that quasi-normal modes and shadows probably the same physics? Because, I mean, I would expect that, say, the ring down is probing the dynamics, while the shadow is more geodesic motion. I mean, I understand the aconal limit, but for example, there might be cases in which the space-time is the same in two different theories, and therefore there will be the same geodesics, but the ring down of the same solution is different because the dynamics is different. In that case, there will be a different ring down.
I think I partially agree with you when you say when you claim what I said is imprecise, but for a different reason, which you know very well, and which is the fact that the ring down may also be sensitive to near horizon effects, to what we call echoes, and those don't lie near the light ring. On the other hand, I think regarding the point you're actually making, I think the effect of the dynamics doesn't impact on the frequencies of the quasi-normal modes, but I would expect it to enter in the excitation coefficients of the various modes. That's the way I see things. So during the ring down, I mean, if you neglect the time span really across the merger, what you really have is a perturbed black hole. So you're really sensitive just to the background geometry. Then if you try to enlarge the ring down by including also the times near the merger, then I agree that the dynamics may be important. But if you focus only on late times, I believe the effect of the dynamics is only included in the excitation coefficients. I might be wrong, but
I think there are counterexamples. For example, I don't want to steal time, so maybe we can discuss this later. But there are theories like dynamical Chern-Simons gravity in which static black holes are Schwarzschild and they have different modes, but the geodesic structure is the same. Maybe it's too technical. We can discuss.
Yeah, no, that I agree. But then you change. These are theories where you change the principal part. Yeah, so that is true. But then I don't know how to study the dynamics of those theories, because the only way I think in which quasi-normal modes may not be sensitive only to geodesics is if you change the principal part of the evolution system, right? And Chern-Simons, in fact, is an example of that. Then I don't know how to study the dynamics either. But yeah, it's well, maybe we should talk about this later. Yeah. You might be right, but I have a well, maybe we can talk about this later.
Okay, there is just we have time for another question, and there is Demosthenes Kazanas.
Okay, let me turn on my camera so that you'll be able to face your accuser.
I can't see you because I'm sharing my screen.
You cannot see me. Well, I don't know. Well, then you won't be able to face your accuser. Anyway, you mentioned about the sensitivities there, S1, S2, and well, if a binary pulsar, the two neutron stars, they have roughly the same scalar charge. So S1 and S2 are, I don't know exactly how close they are, but they're close to each other. So the question is, does that automatically imply that the absence of scalar fields in those neutron stars? And actually, one more point before I quit. If you have a massless scalar field, that was done the first time by Buchtel, but it was discovered several times after that, rediscovered. The deviation from Schwarzschild is at order with scalar field is at orders of v over c to the 6th, not to the 4th. So do we know that there are no scalar fields in the sun? Have we tested the rotation, the velocity of the Earth relative to the sun to v over c to the 6th? So I will stop and I'll let you reply. Thank you.
Okay, so regarding the first point, when I say binary pulsars was admittedly a bit imprecise, there are many systems in which you observe a pulsar and a white dwarf. And those systems, for those systems, because the white dwarf has a very low compactness, the scalar charge is 0. And those are the systems that place the best bounds on dipolar radiation. Yeah, I think you're referring to the relativistic double pulsar. The relativistic double pulsar is an interesting example where, yes, there is very little, if any, dipolar radiation predicted in scalar tensor theories, but also it's a very fast, it's a very low, small, short period system. So you can actually, these theories, these scalar tensor theories predict that there should be deviation from the quadrupolar emission as well. So you can actually, you're sensitive also to corrections at 0 PN order. So the relativistic double pulsar is also very useful for testing these theories, although through the next post-Newtonian order. This is the answer to the first question, although admittedly the best bounds come from white dwarf neutron star
Thanks.
systems. As for the how I mean, I'm not sure I understand what you mean by just a massless scalar field. We have to specify how we couple it to matter.
GR plus massless scalar field. That's
but I don't believe
no well-known exact solution. But anyway.
Yeah, but in the solar system we got only to 1 PN order. So we can't, so I don't believe V over C to the 6. It depends how you count the PN order, but if it is 3 PN order, there is no hope in the solar system. That's a short question, because velocities are 10 to the minus 3C in the solar system.
Thank you.
At most. No problem, my pleasure.
Okay, let's move to the next speaker. I want to remember you, Enrico, that there are 2 questions for you in the chat.
I'm sorry, I couldn't monitor the chat. I will reply on the chat.
Then now we have Asimina Arvanitaki with searching for ultralight boson with black hole super-radiance at ngEHT. Please.
I need to unmute myself and you can see me. Thank you, Mariafelicia, because you said my name perfectly. So that doesn't.
Oh, wow.
Anyway, so in this talk, thank you very much for having me, first of all. In this talk, I will, okay, let's see, does it work? Okay, I click, it works. I will discuss how an effect that is known as black hole superradiance becomes a probe of ultralight bosons, particles, what I mainly be focusing on, particles of spin 0 or spin 1, between masses of 10 to the minus 20 and 10 to the minus 10 eV. I mean, these are very light particles. And the reason is these particles correspond to the horizon size of astrophysical black holes. In this talk, I will describe how, first of all, I will give you motivation why these particles, you should expect these particles to be there, perhaps. And I will explain also how this effect of black hole superradiance affects the evolution of astrophysical black holes to become a probe of the presence of these ultralight bosons in our theories. So the first, the best motivated, perhaps, very light particle, and we're talking particles that are much, much lighter than the rest of the particles of the standard model, is what is known as the QCD axion. Now, in the standard model Lagrangian, we know we can add a term similar to what you see here, and I apologize to the particle physicists. This is not how the term appears in the standard model Lagrangian, but for the strong interactions, it's a term that mixes the electric field and the magnetic field of those interactions, and thus is CP violating. Now, if that term was there, and we expect it to be there because CP, charge and parity symmetry, are not good symmetries in the standard model, it would produce an electric dipole moment for the neutron that we should have seen already. The fact that we haven't seen it yet places, in fact, an experimental bound on this parameter theta that determines the size of the effect on the EDM of the neutron to be less than 1 part in 10 to the 10. And this has been a problem for a long while. So the solution that was proposed now almost 40 years ago, in fact, is to turn this theta parameter to a dynamical field, which is known as the axion. And its cosmological evolution naturally relaxes the value of this theta parameter close to 0. This axion, this particle, which is called an axion, gets its mass from non-perturbative QCD effects, and its properties are determined by what is known as the axion decay constant, which, if it's close to the Planck scale or the GATT scale, you find that the mass of the axion corresponds to a Compton wavelength of roughly 3 kilometers, which is the size of stellar mass black holes. Now, if you go, I should say here, this is an excellent experimental target because its properties of these particles are only determined by a single parameter, this decay constant, and it's also an excellent thermometer candidate, independent of what I'm going to talk about today. Now, if you go to even bigger extensions of the standard model, you will find that the axion comes with partners that have similar property to it. And in particular, if you think about string theory, you find that, in fact, you may have many copies of the QCD action. This is because in string theory, there are three important ingredients for the theory to be mathematically consistent. First of all, you need extra dimensions. Then there are fields that live in these extra dimensions, gauge fields. And finally, you need to compactify these extra dimensions in order to give rise to our four-dimensional world. Now, there is different ways you can compactify. These extra dimensions can be compactified simply on a sphere or a torus, or the complexity, the shape of this compactification of the extra dimensions is only limited by the imagination of the people that work those compactifications out. So the more complex the compactification, the more partners of the particle, the QCD action that I mentioned before, you will find. This complexity is, and their mass, in fact, at tree level, you expect these particles to be completely massless, but they do get a small mass, usually from non-perturbative effects. So there are three classes of particles we could be talking about that arise from, that can arise in string theory from these compactifications. You could have spin zero particles with properties similar to the QCD axiom that I talked about before. You can have spin one particles whose properties are quite similar to our ordinary electromagnetic photon. Nevertheless, they have a mass. The only difference is that they have a mass. And there is also another class of particles. Now, these particles are again scalar. They're CP even, unlike the axion, that determine the size and shape of these extra dimensions, as well as the values of the fundamental constants. And they go by the name of dilaton, moduli, and the radian. Now, all these particles have very common characteristics. They couple extremely weakly to the standard model if you consider couplings beyond the gravitational one. They can be extremely light, which is also related to the fact that they couple extremely weakly to us. And in principle, there are constraints in these couplings that come from astrophysics for Big Bang nucleosynthesis from the CMB that I will not talk about today. What I will focus on today is their purely gravitational coupling, their pure gravitational coupling that can affect the evolution, as I said, of astrophysical black holes. And for the purposes, of course, of this talk, I will try to focus on supermassive black hole because these are the black holes that ngEHT will be studying. Now, the effect of black hole superradiance is not special to GR. All you need, in fact, is a system with a dissipation. And this is a very simplified cartoon that I will describe now. Imagine you have a cylinder that's rotating and it has a rough surface. Now take a little ball and scatter it tangentially off the cylinder. Now, if at the point of contact, the cylinder is moving faster than this little ball, the ball, after it continues its evolution, will slow down after the scattering event. But if the cylinder is moving more slowly than the ball at the point of contact, the force of friction will not take away energy from the ball, but will give it energy. So in fact, you will see that this is a process where dissipation naively gives out energy instead of taking energy away. Now, a similar thing can happen for waves, and the first version of superradiance, one of the first versions of superradiance was actually worked for electromagnetic waves. Now, the analog of the friction-full rotating cylinder was taken by a conducting rotating cylinder, meaning there is a finite resistivity. So you have, this is the analog friction for electromagnetism. So if the rotational velocity of the cylinder is slower than the angular velocity of the scattered electromagnetic wave, the wave comes out with larger amplitude than what it came in with. So this is an amplification process, again, coming from the fact that you have dissipation. So for black holes, and this is where looking from the black hole, or a substance of the black hole, looking from it from above, the role of the absorber is played by the horizon. So you can take a gravitational wave or an electromagnetic wave, scatter it from the black hole, and you will see that the wave comes out, if the angular velocity of the wave is larger than the angular velocity of the black hole, you will see that the wave is, sorry, the opposite. So if the angular velocity of the wave is less than the angular velocity of the black hole, you will see that the wave comes out amplified. So this is a process that extracts energy and angular momentum from the black hole. Now, back in '72, Press and Turkowski wrote a very amusing but kind of useless Nature paper where they said, okay, let's repeat the scattering experiment from waves, but first surround the black hole by a perfectly spherical mirror. So what you will see is that the wave scatters multiple times from the black hole. Eventually, the amplitude they found will grow exponentially, and the radiation pressure eventually will make the mirror explode. So this is what they call black hole bomb. Now, this is not, of course, a realistic situation for astrophysical black holes, but if you have the important ingredient here for this exponential growth, in fact, is that the wave, the electromagnetic wave that Press and Turkowski was using is a boson, spin 1. So if the boson has a mass, you find that the mass plays the role of the mirror because you can create a bound state with a black hole. So what will happen is if you have a fastly rotating black hole, and it's in the right mass range, basically what you require is that the size of the horizon of the black hole is similar to the quantum wavelength of the particle. You will see that the black hole will spin down. At the same time, you will create a wave, a scalar, coherent scalar wave, occupying the bound orbit around the black hole. Now, in order to understand what this bound state looks like, you don't have to go very far. Unless you sit very close to the black hole, the potential is 1/r. And in fact, a lot of the dynamics, so you can think of this bound state as the analog of a gravitational hydrogen atom, where instead of the electromagnetic force, the binding is done by the gravitational force. So you can define a fine structure constant, which is basically the product of the Newton's constant, the mass of the black hole, and the mass of the boson. You can also, uniquely, the levels are quantized. So for bosons, for spin 0 particles, you only need the principal, the orbital, and the magnetic quantum numbers, and you find the energy is quantized. So it goes like the same, you find the similar formulas for the Rydberg in the hydrogen atom. Now, there are very important differences between this gravitational atom and the electromagnetic hydrogen atom. Actually, one of the most important ones that's also responsible for a lot of the signatures is that instead of having fermions occupying the bound states, which have the Pauli exclusion principle, you have the levels, the bound states are occupied by bosons. So the occupation number can be much larger than 10 to the 77, which is more than if you count, which is larger than the number of protons that you have in all the stars in the universe. Now, the other very important point is that because you have the horizon, instead in the presence of the black hole, you have to impose ingoing boundary conditions. For the hydrogen atom, when you solve for the wave functions, you have to impose regularity at the origin. So this is, and this is the very important fact, because you find that when you solve for the eigenvalues of these quantized levels, what you find is that, in fact, the eigenvalues have a small imaginary part. So you turn a Hermitian problem to a non-Hermitian problem. And for states that satisfy the superradiance condition, as I mentioned, you need the rotational velocity of the bound state, the angular velocity of the bound state, to be less than the angular rotation velocity of the black hole. You find that this imaginary part leads to an instability in the Klein-Gordon equation. And just to reiterate what I said before, this is a very general effect. It doesn't necessarily only happen for black holes. It's just for black holes, it becomes more, it grows much faster because things are relativistic, essentially. So now the important thing to know is, okay, how does this thing happen? First of all you need is some sort of quantum fluctuation. You don't need any pre-existing cosmological abundance of these bosons. As long as they're in the theory and they're in the right mass range to affect the evolution of astrophysical black hole, they will do it. The only, of course, the important scale is how fast does this stability happen. And here you see some numbers for when the quantum wavelength is small compared to the size of the black hole. This time scale goes exponentially with essentially the fine structure constant of the atom. When the quantum wavelength becomes large compared to the size of the black hole, it depends on a power law on the fine structure constant, and it's slightly bigger for spin 1 particles than it is for spin 0 particles. So if you look at how fast this thing can be, it can be as short as 1 second for spin 1. And this needs to be compared to the dynamical timescale of black holes, which is 10 to the 8 years. So even though you would say, oh, this is much slower than the infall timescale, the dynamical evolution timescale for astrophysical black holes is something much longer. So the effect has a lot of time to grow and affect the evolution of these black holes. Now, for the HT, just to give you some numbers of the range of mass of interest, for Sagittarius A star, which is roughly 10 to the 6 solar mass black hole, this range corresponds something between 10 to the minus 19 eV and 10 to the minus 16 eV bosons, spin 0 and spin 1 particles. For the M87, which is a much heavier black hole, in fact, roughly 1,000 times heavier, this corresponds to something between 10 to the minus 21 eV and 10 to the minus 20 eV. The range is different because basically M87, it's a much bigger black hole, so the infall time is much longer. So if you compare this to the accretion timescale, it probes a smaller range. Nevertheless, it's still an interesting range of masses. So how can this effect evolve? How do you understand the dynamics? So first of all, you need to take into account how fast the superradiance stability happens. You need to take into account the black hole dynamics. In particular, perhaps the most important scale is the accretion time scale. You also need to take into account, why is this not working? You need to also take into account that because it's a gravitational atom, as I described, you could have dynamics associated with the fact that different levels of this gravitational atom are occupied. In fact, some of the most interesting signatures is gravitational wave emission. So you could have gravitational wave emission when bosons transition from one level to the other. You can also have gravitational wave emission through boson annihilations to a single graviton. And in fact, this is something that's extremely interesting in the context of LIGO, for example. This happens because the bosons that are relevant for these effects are their own antiparticles. They don't have a conserved quantum number. So two particles in the cloud, from a particle physics point of view, can annihilate to a single graviton, which frequency roughly twice the mass of the boson. In in more GR terms, it means that the energy momentum tensor has a quadruple component that oscillates with frequency twice the Compton frequency of the corresponding to the mass of the particle. Now, another thing that I don't have time to talk about, for these bosons can also have self-interactions which can affect the evolution of the superradiance, but at the same time, they can also give rise to interesting signature, and that can give signatures to other terrestrial experiments that are in principle designed to look for dark matter. So this is something that people should keep in mind, but I don't have time to talk about it. So how does the thing evolve? So as I said, the superradiance condition is a kinematic condition. So for every a given axion boson mass will affect more than it doesn't. The mass of the axion doesn't have to the Compton wavelength of the axion of the boson doesn't have to match the size of a black hole. So this is a plot that shows this. So this is a plot that shows the spin of the black hole as a function of the mass, and here in blue you see the different region that can be affected, and each different level that is that can superradiate, assuming that the time scale is faster than the accretion time scale. So this is for stellar mass black holes. So let's assume that this black dot is a black hole that was just born with high spin. So in this case, the L equals 2 levels is the one that satisfies the superradiance condition. It will grow, and then it will stop when it no longer, the growth will stop when it no longer satisfies the superradiance condition. At that point, you expect a few percent to 10% of the black hole mass to be to actually occupy that level. Now, when you reach the point, L equals 2 level is can no longer superradiate, but the L equals 3 level, which grows much more slowly, will begin superradiating. Eventually, and so forth, eventually you will be jumping down these curves till you reach the point where the superradiance rate is much more slowly than the accretion time scale or whatever the dynamical time scale of the system is. Now, this is for stellar mass black holes. If the black hole is growing by accretion, you will be in fact tracing the outline of this blue region, and that's a bit subtle there too, but adiabatically as the black hole grows. Okay, so now you can place constraints to you can use astrophysical, people have measured the spins in X-ray binaries and some supermassive black holes. You can try to place constraints from this spin down effect. You shouldn't see, if there is a boson in a certain mass range, you shouldn't see fastly rotating black holes. And this is what you see here, some data points for stellar mass black holes, and it's already disfavoring a range for the QCD axion that I talked about earlier. You can perform similar analysis of spin 1 particles, and here you see on the right, you see what the disfavored region is for different X-ray binary objects. And this is, and on the left, you see a disfavored region for supermassive black holes. Now, there are subtleties with this. So how do you go about, should you take them even seriously, these exclusions? First of all, in order to be able to place from a given black hole a constraint on the spin, you need to know when was the black hole formed. If you don't know that, you need to know its most recent history. How much is it accreting? Are there any other close, strongly gravitating objects that can disrupt the growth of superradiance and make it not go? When was the last violent merger event? The other thing you need to know is the systematics of these measurements. And in fact, the systematics we found that the systematics are much more significant for supermassive, for the current spin measurements of supermassive black holes. So you need to know what the error bars are in the spin, what are the error bars in the mass, are the error bars even Gaussian when you do the analysis, and should you even trust those measurements? So in fact, in general, when you look at supermassive black holes, the range that is relevant for the ngEHT, the black holes that the ngEHT is observing, you should take those exclusions with a grain of salt. And I think this is in fact where EHT and next generation EHT could be much help, because the spin and mass measurements that they would be provided, I believe, will be not subject to the same systematics of spin and mass measurements attempts that have already been done in the community. Now, to end, there is another interesting thing that can happen. This is that's relevant for the EHT, is the fact that you will see the cloud carries a significant fraction of the mass of the black hole. So if there is a cloud around the black hole, you will see modifications of the near horizon geometry. First of all, you will see a time-independent modification, which kind of has been studied, and actually Enrico will be similar to kind of the things Enrico talked about earlier. The most interesting thing, I think, is a time-dependent modification of the near horizon metric. And this is something actually that has not been worked out, and I think it will be very interesting to do so. So first of all, as I mentioned earlier, because these bosons do not have a conserved quantum number, basically they're on their own antiparticle, there are modifications of the near horizon metric that appear at frequencies of twice the mass of the particle. And that corresponds for the time, for the Sagittarius A star, it corresponds to a time scale of a few seconds. Now, if you have more than one levels of this gravitational atom occupied, you will also see a time dependence in the energies that comes in the energy splitting of these two levels. So if you were to convert it into time scale for Sagittarius A star, this would correspond to something like tens of minutes. For M87, you just need to multiply these numbers by roughly a factor of 1,000 to give you an idea of the time scales. Now, as I said, I haven't seen this worked out properly in the literature. I believe this is a good thing to actually simulate and see these time-dependent effects are going to be kind of like a smoking gun of superradiance. So these will be very interesting to actually work out how big they are and what is the relevant range for the EHT, the black holes that the EHT can observe. So I guess for superradiance, the interesting thing to know again is how well can you measure the spin and the mass of the black hole with EHT? How well can you measure the near horizon geometry? And how does looking for time-dependent effects that are kind of unique for superradiance change this type of analysis? And again, given that in order to be able to not only look for signatures, perhaps being able to place constraints, how much can we learn about the history of the black holes? And with this, I want to end with this, and also with a general comment that black hole and I didn't have time to talk about this. Black hole superradiance is an effect that has extremely a wide range of signatures that can affect not only gravitational wave detectors, but as well can have signatures in dark matter detectors. So there can be a synergy between EHT and a wide variety of laboratory and astrophysical observations that can shed light to the existence of these very well motivated ultralight particles. Thank you.
Thank you for this interesting talk. Do we have any question?
We have a question in the chat.
Yeah, there is several questions.
Yeah. Okay, no, there are two. Razie Henami, please go ahead.
Yeah.
Hi, Asimina.
Hi, yeah.
That was very wonderful talk. I have a few related questions. About the time scale that you mentioned in I think the last 3 slides of Sagittarius and M87. I was wondering, can you give us a little bit of actually more intuition about how do you get these tens of minutes for Sagittarius, for example?
Good. Okay, good. Yeah. So it's just take your, let me see if I can scribble something on screen. It's going to be crappy handwriting, but so basically the energy splitting, right? I talked about them. It is very close to a hydrogen atom. So the energy splitting, let's imagine you have the n equals 1 level and the n equals 2 level occupied. So the energy splitting will be going like alpha squared, sorry, this is very bad scribbling, over 2, this is the mass of the boson here, n squared, right? Where n is the principal minus the energy of 2n plus 1, right? So when you plug this in and you plug the mass, as I said, for Sagittarius is something between 10 to the minus 18 and 10 to the minus 16 EV in mass. If you were to convert it in a time scale, this energy difference, and for alpha roughly, because you needed to satisfy the superradiance condition, it will come out to be roughly 10 seconds. This is 10 tens of minutes for the energy split. It's just regular, this is just a difference, just like the hydrogen atom, but at a completely different, much bigger scale, meaning everything becomes, does that make sense?
Yeah, exactly. Because actually, if you go back a few slides before, I think that you had a very pretty plot that was about the black hole spin versus the supermassive black hole mass. That was the few slide before. I think you can just clear them off, but yeah.
Sorry, let me try to go back, but my thing is not working so much now. Let's see.
Oh, okay.
Let me stop annotate. Let's see if that helps. Okay, yeah, that works. Okay, so where do you want me to go? Here?
Yeah, here, right? So yeah, that was no,
here, this one.
So when you actually talk about the black hole spin change at different levels that you basically occupy by your boson, I was wondering why there is not too much of the overlap between these shaded lines. In another word, I was wondering, is there any possibility that instead of going more like horizontally, we go more like vertically down and just...
So here you move, so for stellar mass black holes, you do move vertically. So the mass doesn't change much. So
that was something that I didn't really...
No, so it's going down like this in each stage. Now, for things that grow by accretion, because things are more adiabatic, you may be tracing the outline of this region. So this, what I have here is a very, let's call it what I prefer to call the cleaner case of an astrophysical, of a stellar mass black hole that just got born, and then you have things just, and the reason you move vertically is what I call the ballerina effect. So because you have a cloud that's bigger than the black hole, it's very efficient and carrying angular momentum. So it can do so by carrying only a small fraction of the mass. So you can take a more significant fraction of the spin without taking much of the mass of the black hole. That's why it's kind of vertical here. Does that make sense?
Yeah, absolutely. That makes perfect sense. And can we also get a little bit further down, or is this like this whitest region just before, just actually below?
So assuming that you start from superradiance, no, because you stop when you no longer satisfy the superradiance condition, which is a kinematic condition, or the effect to grow becomes longer than the dynamical, either the age of the universe or the accretion time scale. So through superradiance, there is no way to go further down. In fact, if you look more formally, there are constraints of how much mass actually you can extract from a black hole through a process like this without violating the entropy theorem for a black hole.
Very nice. So, and really the final question, does it also depend on how puffy is your cloud of axions?
I'm sorry, but we don't have much time. Maybe you can discuss in Slack. Andre, also, I am sorry.
Yeah. Thank you so much. Yeah.
Well, thank you, Raz, for your question. Yeah.
Or maybe just if you want to ask, maybe you can discuss.
Andre, please ask the question.
A short one. I understand that you get directly from that effect, you directly gravitational wave signature, but for electromagnetic,
good.
Because you need additional conversion processes.
Yeah, so usually the frequencies that correspond to electromagnetic waves are so low frequencies that they won't even propagate in the interstellar medium, okay? There is though something, so in principle, I don't think, for example, for axions that have generically a coupling to photons, you would expect to see anything exciting. But for spin 1 particles, which are the exact analog of an ordinary photon, you can calculate what the dark electric field is. and you find in huge values. So if you have a small mixing with the ordinary photon, you could have interesting effects, because this is and when I talk about electric fields, I'm talking about a huge, we're talking MEV squared, like oscillatory electric fields. So now these things could affect the dynamics of the accretion disk and or any of the environment. In fact, we suspect at some point they will not, the superradiance will stop because of the strong interaction. Now, we have tried to think about them. We haven't, because of you run into problems with non-linearities there very quickly. I think we don't know exactly how things, you can get all sorts of instability, pair creation instabilities, all sorts of crazy things can happen. We don't know, we cannot say anything concretely. And we have tried to do simulations with Willis, who is here at Perimeter. The simulations gave us things that were, but it's an exact, for spin one, it's a very interesting question. And this is something that no one has worked out properly. So exactly what you're asking. So that's because the electric fields, like if you can run the numbers, they are ginormous.
It's just because of the occupation number.
It's because of the occupation number, exactly. So for me, a spin one boson that mixes massive, that mixes with the ordinary photon, could have very interesting signatures that no one has worked out.
Okay, well, maybe we just talk on that slide.
Yeah.
Thank you again, and let's move with the last speaker, Paolo Pani. Are you ready, Paolo?
Yeah, I'm ready. Let me just share the screen.
Paolo will present new physics on the horizon.
Wait, sorry.
Yes, testing the nature of dark compact object. Please go ahead, Paolo. We are able to see your no.
Yeah, sorry. No, I want to open it properly because it was not full screen.
Okay, good.
Why is not going the way it should? Oh, sorry. Give me a second. Weird. Sorry, I'll open it different. Okay, now it should work. Okay, can you see the slides now?
Yes.
All right, apologize for the delay, and thank you very much to the organizers for having me. So Enrico gave a very nice talk about testing GR with electromagnetic and gravitational wave probes. I will explore a similar issue, and I would like to discuss possible signatures of new physics at the horizon scale, and in particular how we can test the nature of dark compact objects. I will mostly focus on electromagnetic tests, but I will also try to discuss the synergies and the complementarity with gravitational wave observations. And by the end of my talk, I hope that I will provide a clear picture of what I'm showing here in this cover. This is the embedding diagram of a Kerr black hole that shows how the multipolar structure looks like, compared to what is called a fastball, that is a quantum description of a black hole in string theory. And well, by the end of my talk, I will explain why these are different and what we can learn from them. So let me start with some motivation. 60 years ago, black holes were just considered as curiosity, mathematical curiosity of general relativity. Now they are everywhere. So much so that the black hole paradigm, essentially we have now the black holes have become a paradigm, and any object, any compact object heavier than a few solar masses must be a black hole. This also means that any observation showing otherwise will really shake physics to its ground, will imply either modifications to GR or new matter fields beyond the standard model. And I think there are at least three motivations to look for these exotic compact objects. I would call ECOs objects which are not either black holes nor neutron stars. One of the motivations is that they might coexist with black holes in the universe. For example, they might explain LIGO-Virgo mass gap events that are have been detected in mass ranges which are difficult to explain with astrophysical observations, even though there might be astrophysical explanations for them. And also, exotic compact objects might form in the universe in the presence of some new matter field, possible some dark matter field. For example, the axions that Asimina was talking about before could collapse and form self-gravitating objects that are called axion stars, and they have very similar properties to boson stars. A second motivation is actually, I think, stronger, and it is the fact that black holes in classical general relativity have some problems. In particular, they have singularities in the interior. We actually don't know the interior of a curved black hole in general relativity, at least those that can explain observations. And they are associated when trying to merge general relativity with quantum mechanics with the infamous information loss paradox. Trying to solve these issues is required either new physics at the horizon scale, for example, in the so-called firewall scenario, or in some scenarios using non-local effects, or really drastic changes, for example, explaining a black hole in terms of regular horizonless microstates, as in the Fathable proposal that I will discuss in a moment. At the very least, the last motivation is that we want to quantify the black holeness of compact objects in different mass ranges, and we have now very strong probes in, say, the stellar mass range from LIGO-Virgo and other electromagnetic observations, but the Event Horizon Telescope and future facilities will also probe and are probing the different mass range, actually many mass ranges in the supermassive regime. So the first question is, how do we quantify the black holeness, or the shades of darkness of some object? So say that we have some data and we want to quantify whether this is a black hole or not. I think there is at least a two-parameter space. One is the compactness, so how compact the object is, how small the radius or the effective radius of the object is. And this can be parameterized in terms of this parameter epsilon in a sort of coordinate-dependent way. So when epsilon goes to 0, the effective radius of the object is just, say, the radius of a curved black hole. Otherwise, it would be different. The second dimension in this diagram is the reflectivity. We know that the event horizon classically is a perfect absorber, which means that black holes in this diagram sit here. 0 epsilon, so maximum compactness, and 0 reflectivity. Now, exotic compact objects here can populate this diagram differently. We can have objects with relatively small compactness. Here, small means similar to a neutron star or a bit smaller, with no assertion. And this is the case of boson stars. We can have objects with small compactness and large assertion. This is the case of what is sometimes called diffuse Fathable, or large compactness, no assertion, the case of Grava stars, if one believes that they have a hard surface. And finally, large compactness and large assertion. This is the case of tight Fathables. Of course, ruling out this object is much more complicated, because an object is almost as compact as a black hole and absorbed almost as a black hole is essentially a black hole. The big discriminator in this diagram, at least in this dimension, is the presence of the light ring, which occurs roughly when epsilon is of order unity. So objects on the right don't have a light ring, objects on the left can have a light ring, and there are different properties. Of course, this is very model dependent, but roughly speaking, this is the situation. So the question is, how do current and future observations constrain this parameter space, and can we constrain it more and more? So before going to the phenomenology, let me just mention that in GR, there is a beautiful theorem due to Buchdahl showing that this parameter epsilon cannot be arbitrarily small. In fact, there is no continuous limit to the black hole, provided matters satisfy certain properties. And by violating those properties, we can have exotic compact objects. I don't want to enter in details here. Let me just mention that the theorem works for perfect fluid. So if you don't have a perfect fluid, it does not apply. And most importantly, it assumes isotropy or mild anisotropy, which means that strongly anisotropic fluids or scalar fields, for example, violate this theorem. and also assumes GR, so in modified gravity you can have more compact objects. I will now give you two examples which are very representative for exotic compact object that violates the Bugdal limit. The first one is, or they might, the first one are boson stars. So boson stars are a solution to GR, so they do not require modified gravity. GR here, gravity is minimally coupled to a complex scalar field. The scalar field can also be real. In such case, the metric is slowly oscillating in time, but there are no big difference compared to this. Those solutions are called oscillators. The most important point is that it depends on the scalar self-interaction, this theory, and the properties of boson stars depend strongly on this. We have different models. The minimal one is the one that does not have self-interaction. There is just a mass term, and the maximum mass is inversely proportional to this mass term, similar to the setup that Asimina talked about before. The boson field can also be a spin-1 field. In such case, we have Proca stars that have very similar properties to boson stars, with a big difference that in the minimal model, scalar spinning boson stars were found recently to be unstable against rotation, unless they are strongly interacting. So without this interaction, they are unstable, but Proca stars instead are stable. So there is a plethora of models. And here I'm showing the mass, the angular momentum, and the compactness of some rotating solution taken from this paper, showing that some of them can have a light ring. An important point to keep in mind is that, as you can see from this table here, there is a scale in this theory, which is the mass of the field. Of course, there might be other parameters, but the mass of the field really sets the scale. This means that if you have a single, say, scalar field, you can explain boson stars. You can have boson stars in certain mass ranges, but not explain all, say, black hole observations across all mass ranges, because you will need different scales. A second example, which instead is very different in this respect, are fast balls. So fast balls is a paradigm that is it was put forward in string theory, in which classical black holes are interpreted as an ensemble of a huge number of regular horizonless microstate geometry. So instead, the cartoon that you can have in mind is that a single black hole, a classical black hole, is interpreted as superposition of different fastball microstate geometries that are regular. They may have different deformations, but on average, they resemble the classical black hole. So from far away, they are similar to a black hole, but very close, and especially inside the horizon, they are regular, and there is actually no event horizon in these geometries. In some models, some theories, the entire black hole entropy can be explained in terms of the number of microstates. So really counting the microstates accounts for the whole entropy. In other cases, this is not the case. But the interesting thing is that some low energy truncation of string theory really admits huge families of these solutions. So these are concrete solutions to a theory. Of course, it's modified gravity. This is why it evades the theorem. And so it's well motivated in this sense. And another interesting point is that the mass here is a free parameter. So really, just like a black hole, you can explain black hole with fast balls, both when they are, say, tiny or when they are supermassive. The cons are that so far this has been worked out only for extremal charged black holes or for nearly extremal, and the solutions are really extremely complicated. So it's really hard to work with them. There are other open issues that are a bit technical, but they are interesting, and I suggest you to read this nice review by Diane Myerson if you are interested. Okay, let me move to the phenomenology. So the first question we want to understand is, can we really image the horizon of an exotic of an object in order to distinguish a black hole from an exotic compact object? And this question depends a lot on which region of the parameter space we are looking at, especially what is the value of epsilon that we are talking about. For example, imagine that you have an isotropic source emitting isotropically at some distance from, say, a Schwarzschild geometry. if you start having this isotropic source very close to the horizon, what happens is that the escape angle becomes smaller and smaller. In fact, it goes to zero like epsilon. And most of the photons that are actually emitted bounce back and return to the object. So the point is, if this is an event horizon, of course, everything is absorbed. But if there is a surface, something else should happen. But this already shows that not only the radiation is strongly redshifted when the source goes close to the horizon, but it's also the escape angle becomes smaller and smaller. And here again, the light ring is a strong discriminator because the critical trajectory that these photons have before being able to escape is really going around the light ring that is at 3m in this coordinate. So really there is a big difference whether you can go within the light ring or not. And this is the very rough picture to understand many properties of exotic compact objects, including the shadows. I like always to show this paper by Frederick Vincent and collaborators, because this was done, as you can see, years before the Event Horizon Telescope discovery. And what they were studying here is the image of an accreting boson star versus an accreting Kerr black hole, and they are both spinning. The reason why this image is so similar is that in the case of a boson star, there is no horizon, so matter can go within the star and produce a torus around the center in some stable orbit. And so the final image in this case is very similar because, well, most of the radiation that you get is from this region here that is due to Doppler shift basically and relativistic effect. So this already tells you very roughly that distinguish the two is in principle challenging, and there might be also a lot of dirty astrophysics that you want to model properly and be sure about. But on the other hand, it's also promising because you see that there are small features, especially within this region, that can be able to distinguish the two cases. So a rough estimate from these results is that epsilon of order unity, which means having a light ring or not, is something that can be distinguished. This has been studied more in detail. For example, in this very recent paper a few days ago, people play this imitation game trying to study the image of a Proca star, so one of those version of stable boson stars I was mentioning before, versus a black hole. And the outcome here is that the image depends strongly on the inclination angle, the observation angle of your system. In particular, if you look at the system from the polar direction, it looks very similar, especially when blurred with sort of fake noise. While if you start looking at on the equatorial plane is more different. And the reason is that a Proca star is not that compact, so it's much less compact than a black hole, so relativistic effects are smaller, and you don't get the classical shape of the shadow that you get in a black hole in this direction. So the take-home message is that when the echo is not compact enough, you can, I mean, there are appreciable differences. So now, how about accretion? One could argue, so what happens to this matter that if you have an accretion disk goes inside the object? If there is an horizon, of course it's absorbed, but if there is no horizon, it will start accumulating there. So a very simple computation shows that the matter that is accreted is not that much. So suppose that the object is accreting at a fraction f(ed) of the Eddington rate for, say, the entire history of the universe, then the fraction of mass accreted is a few percent of the mass of the black hole for this accretion rate. And to give an example, for Sagittarius A, this number is 10 to minus 8, which means that you get a much smaller number. Nevertheless, what could happen is that the matter starts being accumulating at the center, producing, again, an accretion torus in this case, which accretes itself, and it might actually emit in a way that it can be, in principle, distinguished. And this is the claim of this paper here. Another point to keep in mind is that here they are comparing these Schwarzschild black holes with two boson star models. The compactness of this model, of both these models, is pretty small. So again, an important point to keep in mind is that when the compactness is small, distinguish an exotic compact object from a black hole is simpler. If the object is more compact, especially if it has a light ring, the situation is much different. And I think there will be a talk about this later on today by Duke about this paper who just was put on the archive a few days ago. Another very interesting point was put forward by Broderick and Narayan almost 15 years ago. And so the question is, what happens if instead of having a boson star that is essentially transparent, there is a hard surface? So something that is really totally reflecting radiation. In that case, what will happen is that eventually the accreted matter will reach thermal equilibrium with the surface, and the surface will start emitting thermally. And the absence of this thermal emission can be used to put a very strong constraint on the compactness at the level of 10 to minus 14 in this epsilon parameter. So it's really an impressive constraint. However, this relies very strongly on the fact that there is a hard surface instead of the horizon. Even a tiny absorption at the surface, so if it's not totally reflecting, would deteriorate these constraints quite a lot, and this was discussed in this paper. So moving to the gravitational wave-based test, I really just want to be brief here because this is not the main topic of this conference. And so what I would like you to have in mind is this cartoon showing the different effects that there might occur in an in-spiral merger ring down of, say, a binary system if the two objects are not black holes. So the first effect is that they might have multiple moments different from those of a black hole, which interact gravitationally differently. And this is a high order PN effect. Then they might absorb radiation or might not absorb radiation depending on whether they have an horizon or not. And this also affects the in-spiral. Tidal effects, tidal deformation or tidal disruption also can occur differently in the case of a black hole or exotic compact objects. And in the post-merger phase, there might be different ring down modes. There might be post-merger features like echoes and things that I will discuss briefly in the next slides. So just to sum up what we have learned so far from gravitational observation, well, a lot. The GR and black hole paradigm are perfectly in agreement with all GW data. Maybe the mass gap events needs more careful discussion, but overall everything fits very well. There has been a lot of constraints, especially on the compactness of the object, really just by measuring the merger frequencies, for example, the first event. More sophisticated constraints come from in-spiral merger ring down consistency test, the consistency of the template, GR template, black hole in-spiral and merger. And especially for some events, the first event and some of the second catalog, it has been possible to do black hole spectroscopy. So to measure some, well, the fundamental ring down mode and therefore extract the mass and the spin and try to do really black hole spectroscopy with these events. So the sort of bounds that come from these analyses are possible, I mean, the absence of deviations in the ring down spectrum puts constraints on the echo models. Absence of echoes in the post-merger phase also puts some constraints. One can try to constrain the quadruple moment, the tidal deformability, the tidal heating, and all these effects that enters the waveform. In the future, these constraints will improve, definitely. I think that really the phase transition will occur in the 2030s with third generation detector and LISA, especially extreme acceleration spirals will improve these constraints by quite a lot. Let me just give you an example about the echo ring down. What one could do is already using the measurements of the first event that measure the first quasi-normal modes at the level of 10%, one can put constraints on this two-dimensional parameter space that I was mentioning before in a model that is borrowed from the membrane paradigm. And the first event, so the detection of the quasi-normal modes for the first event excludes in this parameter space all this region here except for this shaded area. So you see that the bounds are at the level of epsilon order 10 to minus 1, and the reflectivity has to be very close to that of a black hole. This parameter eta is related with the reflectivity in this fashion. And this work was was done by Elisa Maggio and collaborators last year. In this diagram, I'm not showing the region when epsilon is very small, because in this case, the prompt going down is essentially identical to that of a black hole. And in this case, another way to put constraint on echo models is looking for these repeated signals, which are called gravitational wave echoes. And they can constrain the reflectivity of the object, because the reflectivity dictates how big these amplitudes are. So not seeing echoes will put constraints on the reflectivity of the models. Finally, let me mention something that is very important for these communities, the multipolar structure of exotic compact objects and how this differs from that of a black hole. So we all know that there is this beautiful theorem, the ngEHT theorem, which tells us that the mass multiple moments and the current multiple moments of Kerr depends just on mass and spin. This, in terms of the shape of the object, means that Schwarzschild is spherical and Kerr is deformed. Here I'm highly exaggerating the multipolar deformations, but anyway, this is the sort of deformation that one would expect. The color scheme here represents the current multiple moments that do not have an analog in Newtonian gravity. Now, in the exotic compact object case, there might be corrections to these multiple moments, even when they are zero for Kerr. For example, the current quadrupole is zero for Kerr, but might be non-zero for exotic compact object, giving rise to shapes that might be still equatorially symmetric in shape, but as you see from the color scheme here, the current moments break this equatorial symmetry. Or you might even have more generic configuration in which everything is broken. This solution is not even equatorially symmetric. Bounds on the quadrupole moment based both on gravitational probes or electromagnetic probes have been discussed in several different papers. They are complementary in certain respect. I think this paper here is particularly interesting because it gives a very thorough discussion of this problem. An interesting result is that there is a sort of hair conditioning theorem for exotic compact object, which essentially tells you that the more compact the object is, the smaller are the correction to the multiple moment. And in particular, when epsilon goes to zero, these corrections have to go to zero either linearly, and these are intrinsic correction, or logarithmically, and these are spin-induced corrections, which is nice because it means that even when epsilon is super small, these logarithmic terms tells you that the correction is not negligible. So it's something that can be used to put constraint. So let me just advertise that all these solutions that I was mentioning here graphically, they are actually publicly available on this web page. We have notebooks. These are analytical solutions that can be used, for example, to do ray tracing or things like that. And this is work done by Guillaume Raposo in Rome. Guillaume just finished his PhD and is looking for postdoc for next year. So if you are interested to hire someone excellent in this topic, please consider him. Finally, I would like to mention that certain classes of exotic compact objects, like the Fatzball that I was mentioning before, and boson stars, not only can have multiple moments that break the equatorial symmetry of Kerr, for example, the current quadrupole, but they can also break axial symmetry. So a crucial theorem in ngEHT is that stationary black holes are axisymmetric. This is not true anymore in other situations, other models. And this is the meaning of the plot I was showing before in my cover slide. Fatzballs, for example, can break axial symmetry, can break equatorial symmetry. Essentially, they can break everything. Interesting enough, the multiple moments, the ratio of some of them are universal in some of these models. Which is a nice smoking gun for deviations from Kerr, and they are also in some cases minimum for a black hole. So if you can measure the multiple moments and they are big enough, this is a clear way to distinguish them from Kerr. I just want to emphasize that if you look at the publication dates here, they are all from last year. There has been a lot of progress in this on this front, and models and phenomenology should be extended in order to accommodate for these new findings. So my conclusions: we are really living in the black hole era. We are all very excited about that. There are new discovery opportunities for departures from classical black holes and possibly new physics. Let me stress that any signature of beyond Kerrness will really shake physics to its ground. I mean, it would be a major discovery. So I mean, we should really consider this seriously. I think there is indisputable evidence for light rings coming from the Event Horizon Telescope, which is, by the way, consistent with what gravitational wave are teaching us. Probably probing the horizon is even conceptually impossible because you need infinite time to make sure that an event horizon forms in a space-time, but we can constrain models more and more. And in fact, probably models with perfect reflectivity, which are not that compact, are essentially already ruled out. So it's not an endless job. Horizons are also very special because they can amplify possible quantum gravity effect. All these logarithmic corrections that I was mentioning before might provide a portal to possible quantum gravity effects near the horizon. And overall, there has been dramatic improvement on echoes on all fronts, and there will be more developments in the future. So we'll close just by sharing this table taken from this living review that I wrote with Vitor Cardoso 2 years ago that gives you very roughly the order of magnitude of the constraints on this parameter epsilon that we have so far. And in the future, these numbers will be updated. I'm looking forward for the discussion to understand how better can we do in the future. So I will finish here. Thank you.
Thank you, Paolo. I'm so sorry, but since the program is very tight, we have to skip the question.
Oh, I'm sorry.
Yeah, but I remind that you can discuss on Slack channel if you want or later. I just still thank everyone for your talk, and maybe Daniel, you can give some announcement about
Yeah, that's right. So I believe the plan is to rejoin at 11:50. So SOC, is there any change on that plan?
That sounds good to me.
Great. So we're going to slide the schedule by 5 minutes. I'll announce this via email. Thank you to all of our speakers in this amazing session.